Hi guys, it's your science teacher here, and in this video I'm going to go through the whole unit, which is chemistry of the atmosphere. So without further ado, sit back, relax and enjoy this video. At the start of the video, what I'm going to do is I'm going to go through the current composition of our atmosphere, and then we're going to delve into the history of our atmosphere, how it was created and how it came to have these current conditions that we have. So if we have a look at this pie chart, you'll see that the largest segment of the pie chart is nitrogen. In fact, our atmosphere is 78% nitrogen. And this often surprises a lot of the students that I teach when I tell them this. And nitrogen is incredibly stable, very unreactive, and once it's in the atmosphere it doesn't leave. It's because of the fact nitrogen is in fact triple bonded. You'll know from, if you understand structure and bonding, that nitrogen puts in 3 electrons to each each nitrogen atom, puts in 3 electrons into the bond, and this makes it incredibly hard to break that bond. Then if we look at the next largest wedge, we have oxygen. And oxygen is obviously vital for life on Earth, and it makes up 21% of the atmosphere. Then the next one, this often surprises people as well. The next largest is argon, and argon makes up around about 0.9% of the atmosphere. Also incredibly stable. Remember, it's a noble gas, full out of shell, not going to react very well with anything. So once it's in the atmosphere, it stays around. And then finally, this smallest wedge, around 0.1%, is made of other gases, including the likes of carbon dioxide and methane. Now, our atmosphere has been like this, relatively stable, for the last 200 million years. And you might ask, well, how do we know that we've had these stable conditions for the last 200 million years? Well, what we can do is we actually look at ice cores. This is samples taken from glaciers, and what we do is we analyze the air bubbles inside the glaciers, and they prove that our atmosphere has been like this for the past 200 million years. But as you're probably very aware, our planet is not 200 million years old. It's actually 4.6 billion years old. This is how old the planet is. So what was its atmosphere like all of these years ago? Well, in fact, when the Earth was 4.6 billion years old, it didn't have an atmosphere. The atmosphere was created due to volcanic activity on Earth. So volcanoes erupted, and these spewed out gases into the atmosphere. And the main gases that came out of volcanoes were nitrogen, carbon dioxide, water vapor, and then we had trace amounts as well, small amounts of methane and ammonia too. So all of these went out into the atmosphere, and this was the current composition of the atmosphere. We're going back now to around about 3 billion years ago. And you're probably asking, how do we know that the chemical composition was like this 3 billion years ago? Well, in our solar system, we have volcanic planets that we can analyze, such as Mars and Venus. And Mars and Venus have similar atmospheres to what we would have had 3 billion years ago due to the volcanic activity that they have. Now, if you know anything about these gases, then you will know what properties our atmosphere must have had. For example, you might know that carbon dioxide is a greenhouse gas. And due to the fact it is a greenhouse gas, the planet would have been very, very hot at this time. and it definitely would not have been able to support life. So, what changes happened, and when did we start to get an atmosphere that starts to resemble a little bit more like what we have today? Well, one massive change is that water condensed and formed the early oceans, and this sparked off a huge chain of events. Once the temperatures on Earth basically got low enough, that water that was present in the atmosphere could condense, and this is what formed these early oceans. And from this, there was a spark of chain events. So let's have a little look at what happened after. As you know, the early atmosphere contained lots of carbon dioxide, and the water condensing was really key in removing some of that carbon dioxide, because some carbon dioxide dissolved into the oceans. And the oceans is actually a massive store of carbon dioxide. Although there was less carbon dioxide in the atmosphere, it still couldn't support life as we know it, because there was no oxygen in the atmosphere. However, that was soon to change. Basically, plankton and algae, very basic marine life, started to photosynthesize. And photosynthesis was what put into the atmosphere oxygen. And this was the next huge change. If you know the word equation or the symbol equation for photosynthesis, you'll know that what's going on is we're having carbon dioxide and we react it with water, and what it makes is glucose, and it also makes oxygen. To balance that equation, you remember the number of the devil: 6, 6, 6. Also, it's important to remember that these plants, when they were growing, were not just storing the carbon, but when they died as well, this carbon started to go into the ground and it was becoming locked in the ground. And we call this locked carbon. Now, this locked carbon over millions and millions of years formed fossil fuels, and it also formed sedimentary rock. As these dead plants piled and piled over onto each other over millions and millions of years, they became trapped in the rocks, forming sedimentary rocks, and also producing fossil fuels. In addition to this, when we started to get more advanced life forms, things like simple fish and even animals, dinosaurs roaming the planet, then when they eat plants and then they die as well, they lock up carbon in the ground just the same. You can actually see locked up carbon inside sedimentary rocks. Here I've got calcium carbonate. Now you can see that it's locked up carbon by adding it to an acid, and what it will do is it will release that locked up carbon. If I added hydrochloric acid, for example, we would get calcium chloride, carbon dioxide, and water as well. Remember, you can always test that you've made carbon dioxide by simply bubbling it through lime water. And if carbon dioxide is present, that lime water will turn cloudy. You remember earlier in the video, I said that for the last 200 million years, the atmosphere has been pretty stable, with small fluctuations in the amount of carbon dioxide in the atmosphere. However, human activity is increasing the amount of carbon dioxide in the atmosphere at an alarming rate. If you have a look down here at the graph, it shows the amount of carbon dioxide in the atmosphere in parts per million, and also it shows the mean temperature, and you'll see that there is a huge correlation between the temperature and the amount of carbon in the atmosphere. Look at the year 2020 here, it's almost 1 degree higher than the temperatures in 1930 and 40, and this can have drastic effects, and we're going to talk about them effects in a little bit. But before, we're going to look at how we are increasing the amount of carbon dioxide. Well, what we're doing is we're burning fossil fuels. I said that over time, carbon becomes locked in the ground when plants and animals die. It takes millions and millions of years to form these fossil fuels, and they've locked this carbon in the ground for millions and millions of years. However, can be released when we burn these fossil fuels. We burn them in order for a variety of different things. We burn them for transport, we burn them for energy as well. And they're incredibly useful. Doing this, we can produce copious amounts of electricity, and we can travel around the world wherever we need to. But unfortunately, with everything, it does have consequences. And here, this carbon dioxide that had been locked in the ground for millions and millions of years is increasing the temperature of our planet. As well as burning fossil fuels, we are also cutting down trees at an alarming rate. Deforestation is also contributing to an increased amount of carbon dioxide in the atmosphere. Remember, we said earlier that plant life, and especially trees, are great stores of carbon. They photosynthesize, removing carbon from the atmosphere. Now, when we cut them down, that carbon is released into the atmosphere, and therefore that will also affect the amount of carbon dioxide in our planet. Now, we know that carbon dioxide is a greenhouse gas, but how do these greenhouse gases actually work? So we'll just have a look at the two main greenhouse gases, and these are carbon dioxide and methane, and basically they act like a blanket around the earth, okay? What happens is the sun's heat energy enters our atmosphere and it warms the planet up, okay? It's called shortwave infrared radiation that enters our atmosphere. And as the planet warms up, it radiates out long-wave infrared radiation. Now, this long-wave infrared radiation cannot travel through this carbon dioxide and methane blanket. It actually radiates it back down to Earth, okay? And this is what's causing the warmth of our planet, is these greenhouse gases re-radiating the heat, the long wave infrared radiation that's trying to escape. Some of it does escape out into space, but a lot of it is reflected back down to the earth due to the greenhouse gases. Now, earlier we said how the amount of carbon dioxide in the planet was increasing, but we never really talked about methane over here, this CH4. Well, methane is put into the atmosphere mainly due to intensive agriculture. It also goes into the atmosphere when our waste decomposes as well. But intensive agriculture is putting large amounts of methane into the atmosphere. And in fact, methane is incredibly good at re-radiating this long-wave infrared radiation. Now, this greenhouse effect that has been going on for millions and millions of years, it's important for our planet. If we didn't have the greenhouse effect, our planet would be too cold to even live. It would be constantly frozen over. However, it's the fact that we are now putting in copious amounts of carbon dioxide and methane into the atmosphere, which is warming the planet at too much of an alarming rate, and it's melting the ice caps. and we're going to have a look at some of the massive problems that can be caused due to changing our climate. Now, it's important to note that climate change has been happening all throughout the Earth's history. As we've looked at, the climate has not stayed at a complete constant. There's always been small amounts of fluctuations. However, what we say is happening now is we say that our world is warming, and we call this global warming. This is the average increase in the Earth's temperature, and this is as a result of this deforestation and fossil fuel burning. So let's have a look at some of the consequences of global warming and climate change that it could have on the planet. So the first one is over here. We're going to look at droughts. We're going to get more extreme weather events taking place. This could be not just droughts, it could be floods as well. Basically, places that don't get much water will get even less, and places which do get a lot of water will get even more. So we're going to get drought in some areas, and we're also going to get flooding in some areas as well. And if we look down here as well, the polar ice caps are going to start melting, and this could cause not just impacts on humans, but it can have a massive effect on the environment and wildlife. Here you can see a polar bear which depends on that polar ice. It now has to swim much larger distances in order to catch food, and the polar bear is one of them species which could go extinct. As well as causing a massive problem for the environment and animals, we're also going to cause coastal flooding. We're already seeing it around the world by the coastline. The fact that we are having to protect it even more, and we are losing parts of the coast at an alarming rate. When considering the effects of climate change, the way my teacher always taught me about it was he considered the sustainable sheep. And what he meant by that was he looked at the social impacts of climate change, the health, the economic, the environmental, and the political effects that it would have. Now, looking at the social effects of climate change, well, these are the effects that it's going to have on people. People are going to die, and people are going to be displaced from their homes. This is obviously a direct link to climate change. As well as this, there's going to be health implications. People living in warmer environments with less access to clean water, that's going to be a huge impact. And also, disease might spread. Think about the malaria carrying mosquitoes. They'll be able to travel further north and further south, and this could cause malaria implications in lots of different countries. Looking at the environmental, well, just look at some of the different animals. They're going to have to adapt to a warming planet, and with the warming planet, maybe it will affect some animals in a food chain, and if one animal goes, then this can have larger implications on that food web. Look at the topic of ecology, and you'll understand this. Economic, people having to move away from coastal environments. There's cities that are huge built by the coastline. Just think about New York, San Francisco, even London is built quite close to the coastline. And then political as well. Think about the impact of how governments are going to have to deal with all these challenges due to climate change. And in fact, you probably see in the news a lot of the time, people's political views may be swayed due to government's stance on how it's going to change and treat the environment. As we prepare to live with a warming planet, we have to find ways of living with this, and we can look at methods of protection, And this is an example of some flood defenses by a river. So like I said, we're going to get more extreme weather events due to climate change, and building flood defenses is going to be incredibly important in protecting some of them key areas and minimizing economic damages and social damages, even causing death maybe in some areas if the flood is that bad. So as well as protection, we also have some prevention methods as well. It's not all doom and gloom, people. Preventative methods can be switching how we produce energy. We can use renewable and sustainable methods of generating electricity that do not produce carbon dioxide. For example, here I've got utilizing wave power or wind or solar. All of these do not rely on burning fossil fuels. They might not be as reliable as fossil fuels, however, they do not produce carbon dioxide, and this is obviously such a massive plus considering how alarming rate we are warming our planet. Now, it's important to remember that it's not just carbon dioxide that humans are putting into the atmosphere. We also have other atmospheric pollutants. And the first one I'm going to talk about is nitrogen oxides. Nitrogen oxides are often put into our atmosphere when we have really hot engines or really hot generators. What happens when you've got really hot engines or generators is naturally occurring nitrogen from the air reacts with oxygen to form these nitrous oxides. I've just put an X there because the amount of oxygen in the compound can vary. An example of one place where this happens a lot is inside diesel engines. This is one of the reasons why diesel is kind of being faded out, is because of the fact that they do put a lot of nitrogen oxides into the environment. And nitrogen oxides are incredibly bad for the environment because they can cause respiratory infections and respiratory diseases in humans. Just think about how many people now have conditions like asthma, and that's due to the fact that we're breathing in so many more different atmospheric pollutants, and it's not good for you. As well as nitrogen oxides, we are also putting sulfur dioxide into the environment. Sulfur is often an impurity in coal, and sulfur will react with oxygen and it makes sulfur dioxide. Now, sulfur dioxide itself isn't too dangerous. However, what happens in our atmosphere is it reacts with water vapor to form sulfuric acid, which is also known as acid rain when it falls back down to Earth. Now, acid rain can have dire consequences on different environments. Here you can see a healthy tree being destroyed due to acid rain. What happens is the acid rain changes the soil pH, and if the pH changes too much, then it can kill the tree. Also, it affects river ecosystems. When acid rain gets into the rivers, it can change the pH, it can kill the fish, and it can also kill other different invertebrates that are in the river or different plant species that lived in that river as well. As a result of this, we are trying to find more alternatives to burning coal. In fact, a lot of power stations now actually burn natural gas because it contains a lot less sulfur in it, and therefore we're putting less sulfur dioxide into the environment. Now, I know that this video does seem a little bit doom and gloom, but well done for sticking till the end, and hopefully you enjoyed it and hopefully you learned a bit which will help you pass your GCSE exams.